usually, I mean, as I said, it depends on the beach, whether it's eroded quickly or not, but in normal situations and after human impact, you don't have such a catastrophic effect. And I want to give you an example. I'm not sure whether it is in this page. Let me see. Because there was this example of, one second, of, let me see, sand bypass. I tell you, and then I try to find, because it's nice to see. There is a typical situation where you can generate a human impact on the beaches that is concerning. Think about a beach, and then about an estuary, which is more or less done like this. And let's suppose that you have a significant along-shore sediment transport in this direction. What happens here is that you have a movement of sand along coast, and due to this movement of sand, and due to the conflict between the waves, the incoming waves, and the incoming water from the river, you have a stronger deposition of sand in front of the estuary, and therefore a bar generates because there is transportation of sand for this brought by this current, and here you have a convergence of incoming wave waters from the river that causes a decrease of energy of this current, of this ocean current, and then you have the formation of a bar. And the bar is something that usually it's formed in front of estuaries. Even if you don't have a significant along-shore transportation of sand, you have sand from the river, and then there is a conflict from the incoming waters, and usually in front of estuaries you have this bar. And the problem in natural condition, what is the problem? The problem is that if you want to navigate, the bar is a problem, and therefore a typical intervention that people do is they bring a wall here, and you see several examples. You bring a wall here in order to avoid the formation of the bar. If you do like this, of course the bar disappears, which is fine, and what happens is that if you have a significant along-shore transport, you get a configuration like this one. And then something like this. And the sand disappears here. And this may be quite quick. And quite quick, I mean like in 10 years. And there is a nice example that is linked on my web pages, but anyway, I will find it later. So, in this situation, what people invented is a sand bypass system, which is a pipe that overpasses the estuary with a bridge, and then through this pipe, they pump sand mixed with water from here to here. This is a sand bypass. And the sand bypass is frequently used in the estuaries. And just curious to see how I put it, because I saw it while I was traveling with the train, and just one second. Because this is a nice example. I think it was in... It was not here. No, it was not here. Just one second, give me a couple of minutes. Let me see here. No, not here. So I think it is here. Okay, this is the link I was. You see, this is the bypass, the bypassing pipe. And this was in New Zealand. It's a project that was done in New Zealand, and it's if one looks at here, and this is. Let me see. I think there is a nice picture. Okay. You see this picture there. Let me increase the size. You see that there is the estuary, and there are the walls. Now you see equilibrium, but basically here you see equilibrium, but before the bypass, given that the sand is moving from the bottom of the picture to the upper part, before the bypass, the sand was accumulating in the lower part before the estuary of the beach, and the sand in the upper part, beyond the estuary, was completely disappeared. And therefore they constructed this bypass. And here, this web page, which is linked on this page here, which that we looked at before, this is interesting. If you have a look to this web page, there is a nice video describing the sand bypass system. It's not very technical. And also there is a page on coastal processes, which is basically you already need this. And then there are also frequently asked questions that are interesting. And there are also pictures related to this project that show the different configuration, but I'm not sure where they are historical images. Here it is. I think there are some pictures that show what was the situation before, but they are taken from the top and I don't see them here. Okay, but I leave to you the opportunity of having a look. Okay, let's go back to our discussion. And okay, before we were looking at this table here. Just before we move forward, I just wanted to tell you that this web page starts with the part that I skipped because we already discussed about it, about the structure of a beach, what is a berm, what is a dune, shoaling. We already discussed this in the last lecture. And also there are some pictures of what is a berm, what is a dune, etc. And then it starts with this. Okay, now we have to focus on estimating erosion sediment transport. This is quite a technical part, which I don't think is difficult, but anyway, this is something that requires a bit of attention. And there are several formulas that are used to estimate the longshore sediment transport. We are focusing on a formula that is called CERC. It's an acronym, but I don't remember what is the meaning. Just let me have a look. I don't remember what is the meaning of the acronym, just okay, I'll tell you, but it is something related to an institution in the United States. So, no, it's not this one. Okay, anyway, let's talk about this formula. And this is the most widely used. There are several other formulas that can be used. And this formula, I like it because it has a physical basis that is quite significant. And basically, it expresses the longshore sediment transport has a volume transport rate. We indicate it with the symbol QL. And also, as I said, it can be expressed in cubic meters per day or year. And there is a basic assumption, and the basic assumption is that the longshore sediment transport is related to the Longshore component of the energy flux, which is generated by waves. So we have a design wave approaching the beach. We have to estimate the energy flux of the wave, and then we express the sediment transport as a linear function of the energy flux. So the flux of sediment is just given by the flux of energy generated by a design incoming wave times a constant. Very simple. And you see that there is a physical basis because it's related, the flux of sediment is related to the flux of energy. But there is also an empirical part, which is just a constant that is introduced to relate the flux of sediment to the flux of energy. So, what do we have to do then? We have to estimate the wave energy, and in particular the energy flux through a surface of a unit area or unit width that we will see. So we have to estimate again the energy of an incoming wave, a design wave. So we need to identify the design wave. It could be estimated as an extreme wave or as a regular wave, depending, regular meaning not extreme, depending on what is the transport you are interested in. If you are interested in the transport originated by an extreme event, you refer to an incoming wave with a 100-year network period, and then you estimate wavelength, wave amplitude, and wave energy. If you are interested in processes that take place in the time span of 1 month, you may estimate a design wave that is a mean monthly wave. At the end of the story, you end up with the identification of a wave with a given amplitude, wavelength, and we have to estimate the energy. I think you already started that during the movement of waves, there is an interplay between potential energy and kinetic energy. So, during the wave phase, we have an interplay, we have an increase of potential energy at the expense of kinetic energy when the wave reaches the top, and then again when the wave reaches the lower level, there is an increase of potential energy at the expense of kinetic energy, and etc. I'll show you a graph. Basically, what happens is this. If we refer to a fluid particle, and basically this is the wave, and let's refer to a fluid particle which is given, for instance, by the red circle, and then you have the interplay between potential energy and kinetic energy up there, where the potential energy is in blue and the kinetic energy is in green. It can be proved that the amount of potential energy, the max of potential energy, which is reached at the top and the bottom, is equivalent to the max of the kinetic energy, which is reached when the particle is allocated on the mean sea level. So this is something that we give for proved, namely the fact that you have the max of kinetic energy, which is equal to the max of potential, we give it for proved. It's an intuition. If you think that the wave conservates the energy, you can derive it by intuition. If you think that the wave doesn't dissipate the energy, and if you think of the red particle basically goes up and down. So when you reach the top, the particle is as velocity 0, and the same at the bottom. So kinetic energy is 0. At the top, potential energy is max. Even at the bottom is max, but I guess that you don't understand why, so let me explain in a minute why the potential energy is also max at the bottom. And when the particle moves, the max of the velocity, when is the max of the velocity, is in correspondence of the mean sea level. We have the max kinetic energy and zero potential, because we refer the potential energy to the mean sea level. We take as reference the mean sea level. Okay. Now, I'm not sure that you get, I'm sure that you get the reason why the potential energy is max at the top. I'm not sure if you get the reason why the potential energy is also max with the same amount at the bottom, because we are used to associate the potential energy with altitude. And therefore, it's difficult for us to understand that at a lower level, so lower altitude, we have a high potential energy. And the reason is that in this system, the hydrostatic law applies. So what is the hydrostatic law? Basically, if you think at a tank that you fill with water, and you fix a reference level, a reference horizontal level, z equal to 0. And okay, let me say, yeah, that's fine. The hydrostatic law says that within this tank, if you sum the altitude z of a given fluid particle plus relative pressure in the liquid divided by the specific weight of the liquid, this is constant. Meaning that if you go at the free surface, you have max z and you have the pressure, which is 0. Relative pressure with respect to the atmospheric pressure is 0, because you are in touch with air. If you get deep into the tank, you have z decreasing, but the pressure is increasing because you have the weight of the water above the particle that puts the particle under pressure. Which means that what we are used to, the altitude energy, potential energy, is converted into pressure energy, but it's still potential, because the particle is fixed, it's not moving. So it is another way of expressing the potential energy, through pressure, not really through the altitude of the body we are considering. The body is the fluid particle. So we are used to think about potential energy in terms of height, altitude. In this case, we decrease the altitude, but we increase pressure, and therefore we don't lose potential energy. If you think about the fluid is uncompressible, water is uncompressible, but think about something, a body that is compressible. If you get the body here on the free surface, the body expands, and then if you bring the body in deep into the water, the body is compressed and accumulates energy after compression. If you release the pressure, the body expands or goes up. So pressure is another way of giving potential energy. So what happens in a wave? And what happens in a wave? In a wave, it happens that if you have the mean sea level here, and you have a particle fluid that is here, what happens is that here you have a pressure of water, the particle has velocity 0, the altitude is low, but here you have a pressure of water, and the pressure of water is given by pressure can be computed depending on the liquid that is above, and the liquid that is above, it's this column here. The result is that this particle of water has pressure below it, much lower pressure above, and therefore lifts. And this is the movement of the wave. Why the wave, after reaching the bottom, comes up again? Because it's the pressure of this upper part of the wave that pushes the wave up. And therefore, if the particle has energy to lift, this is the potential energy. So it can be easily seen that if you have this is what we call in my pages, this is the wave height, yes, and I think in my pages it's called HB. So what is the pressure? The pressure is HB divided by gamma. And this is equivalent to the potential energy that the fluid particle has at the wave top. I hope this is clear. If it's not clear, I can explain it in better detail. And but in order to explain it in better detail, I should recall back concepts related to the conservation of energy in the fluids, Bernoulli theorem. So I don't think it is the case. Anyway, if I would like that you think about it, and if it is clear the meaning of that graph, if it is clear that still the potential energy is very important and high at the wave bottom, that's fine. And next week you tell me. Instead, if next week you are still in doubt and you would like me to explain with more detail, I can easily dedicate 15 minutes to get back the Bernoulli theorem, conservation of energy, and then I prove to you that the pressure energy, HB divided by gamma, that the particle is here, is the same energy Z given by altitude that the particle has here. Okay? So, let me go back. Okay, so let's estimate then the wave energy of a plane wave, design plane wave. Okay, now let's look at this relationship in detail. And don't be concerned, it's just something that we can easily see. First of all, let's compute the energy of the wave. Let's refer to unit horizontal area beneath the wave, and let's compute the energy of the wave by referring to the mean sea level. And therefore, let's compute the potential energy. So energy is indicated by EB, per unit horizontal area. EBP is the potential. So let's compute first the potential energy. So in order to compute the potential energy, we refer to even wave. And if this is minus EB, this is 0, and this is okay, let me indicate with eta generic height. Basically, the potential energy of a column of water is given by, for each For each fluid particle, we compute the specific weight, which is the product of rho times g. Rho is the mass density of seawater. So the specific weight times z in the z. And we integrate between, let me indicate, so eta has the overall, we integrate it between 0 and eta. Or minus dB and eta along the whole column. So basically, this is minus dB. We compute the integral of a column of water with unit horizontal area. The integral of the product between specific weight and height of each fluid particle. And we need to compute the integral of all the fluid particle in a column of water, again of unit horizontal area, with between minus dB, which is C bottom, and eta. And given that we want to refer the potential energy to the mean sea level, we have to subtract the integral between minus dB and 0. Be careful, we want to compute the average of the first integral. In general, we want to compute the average of this energy over a wavelength. And therefore, there is an average sign above the integral. But you don't see the average sign of the second integral because minus dB and 0 are fixed. And therefore, you don't need to take the average. The wave height eta is varying along the wave phase, and therefore you need to take the average. So basically the first integral is computed between the sea bottom and the wave height, which varies along time. So before correcting, I indicated it here, which was not wrong. Now I indicate it on the top, but eta prime, after some time, is changed. It changes along time, of course. And therefore you have to take the average along the wave phase, because I am interested in the average energy that is transported by the wave. Okay, and therefore, again, note that the second integral, the minus integral, I don't need to take the average because minus dB and 0 are fixed. Okay, so what is the result of that integral? The integral of rho g z in the z. What is the result? First of all, this is equal to rho g are constant, integral between, okay, let me skip the limit of z in the z. Okay. Again, rho is mass density of water, g is gravity. Keep in mind that rho g is equal to specific weight, which is what we want to consider to compute the potential energy. What is the result of this integral? Again, this is rho g. It is 1/2 z squared computed between, in that case, is minus dB and eta. And then I have to take the average. Okay? Okay, so basically, and let me continue. So the result of the integral, if I look at the first one, is what is written there. So E B P is equal to rho g. Again, let me compute 1/2 z squared between minus dB and eta, and this is average minus rho g and this is the minus integral. Again, 1/2 z squared computed between minus dB and 0. Okay, so I can split this one, and I can write EBP, sorry if you can see, EBP is equal to rho g, again, I think, yeah, I can do in this way, 1/2 z squared computed between eta and 0, average, plus rho g 1/2 z squared computed between minus dB and 0. I splitted this one in two parts. I don't need to put average here because dB and 0 are constant, minus this one, rho g 1/2 z squared 0 and minus dB. And these two compensate each other. And therefore, what I obtain, be careful because here, what I obtain is EBP is equal to rho g 1/2, it is still constant, so eta squared average, which should be, yeah, same thing, and then I can take rho g, the constant, out of the average sign. This is equal to 1/2 rho g eta squared, sorry, eta squared average. Yeah.
Prof, the second integral from minus dB to 0 doesn't represent the potential mean energy density in Calm water, like without.
Yeah. That's true. And we are interested in computing the excess of energy with respect to calm water. This is why we subtract it.
But then why don't we directly integrate instead of minus dB mu minus mu mu?
Yeah, because that's true. That's true, because under the assumption of a regular wave, minus dB is equal to minus eta. But if you don't make this assumption, this is more general. But you're right. Under our assumption, because I said at the beginning, we assume that the wave is regular, so I could have put there minus eta and no. No, sorry, one thing. It is, so your question was, your question was, why don't we integrate between what extreme of integration? Minus eta and eta.
Instead of including a term which is the seawater depth.
Because you know, if you refer to the overall potential energy of the water column, you have to go up to down to the sea bottom, and then, given that we are interested in the surplus, in the energy that exceeds that of calm water, then we have to subtract that of calm water. So, and if you go between minus eta and eta, you compute the potential energy of the wave, and yeah, okay, you could do the same. Like I compute the potential energy of the whole wave, and then I remove what corresponds to the calm water. So I remove from minus eta to 0. Yeah, it will be the same thing. And I think that in this case, this is the usual and classical way to derive this formula. I think that it's clearer because you compute the potential energy of the whole water column, and then you remove from the sea bottom to the mean water level. But of course, you could also start from minus eta. I think it would be the same. in my opinion, would be less clear, because you could also start directly from the mean sea level. I mean, you could also start from there without saying anything else. Just saying, I am interested in the exceedance of energy with respect to the mean sea level, so I start integrating from the mean sea level. And in this way, I think it is a bit more comprehensive, but you could also start from zero to eta. Do you recognize that it will be the same? Okay, but what is the result of this? The result of this, and I would like to compute it before we stop for the break, is, let me indicate then eta with let me refer to the amplitude of the wave. Let me indicate with A the amplitude of the wave. The result is 1/4 rho g A squared. And this is something that I would like to prove. So the average of eta squared, which is the eta is the coordinate of the elevation of the free surface during the wave phase. The average of eta squared is equal to 1/2 A squared, where A is the wave amplitude. In order to prove it, I think the easiest way is to open an Excel sheet and compute what is the average of eta squared. Eta can take positive and negative values because it's the elevation of the water surface with respect to the mean sea level. So let me open an Excel sheet and then we break. I use the yellow office here, let me see. Okay, let's